This video is part of the Commercial Building Electrical Design series, continuing our look at power distribution design. And this video we want to start looking at panel design, and in particular we want to talk about demand loads. So again, looking at the snapshot of where we are, we've done delivery systems, we've looked at common materials used, we've looked at branch circuit design, and now we're going back and looking at panel board design. So now that we have a firm understanding of how to properly size all the components, that is the breaker, conduit, wire, ground, etc., for various types of branch circuits, we now need to look at how we supply all these circuits from a panel board. Breakers are used in panel boards to derive the various branch circuits from the bus in the panel board through a tap connection. Since we can have as many as 42 branch circuits served from a single panel, we now will look at how these loads are added in the panel and how to properly size the panel and its associated feeder. So with as many as 40 loads being fed from a single panel board, it seems logical that depending on the load types and uses, except for some special cases, it is highly improbable that all loads will be fully utilized all the same way at the same time. This being the case, the National Electrical Code has certain prescribed diversity factors that can be applied to various load types when calculating the total load on the panel board. These diversity factors are defined in Article 220 of the National Electrical Code. So we will now take a look at some of these more common load types and their factors in the next few slides. So receptacle loads. So the first type of load we want to look at are the commonly used loads of general receptacle loads. In a panel board, the first 10 kW of receptacle load shall be counted at 100%. After this, all load above this 10 kW shall be counted at 50%. For example, if we have a panel that has a total connected load of 18 kW of receptacle load, the load we would use for sizing the panel board and feeder would be 10 kW plus 8 kW times 50%, or 14 kW. So instead of the 18 total, we would be utilizing, we'd only count 14 kW for what we expect the load on the panel to be. And so that would be 38, almost 39 amps if we were doing a 208 three-phase panel. That's compared to almost 50 amps if we took it at 100% all the way. So 18 kW would give us 50, but we only have to count 14. So you can see that reduces the load on our panel by over 10 amps. Next load type is lighting. Remember, this is a continuous load. So as we've already seen when sizing branch circuits, all continuous loads including lighting loads, must be sized at 125% of the full connected load when used in sizing a panel or feeder. So for example, if a panel is feeding a lighting load of 12 kW, then we have to take that at 125%, or 15 kW. So that's going to give us about 41 amps, almost 42 amps on a 208 three-phase panel. This is in contrast to 33 amps that we would have used if we just used the load at 100%. So we're actually taking more, or accounting for more amps than we'll probably see from the lighting. But again, this is because we're expecting this to generate more heat and have more heat accumulation. So we actually size it differently for that reason. Again, remembering that the heating loads are generally, we need to remember that heating loads are generally considered as continuous loads in load calculations. So this can vary though. You know, if you live up north, you know, the heat definitely could be expected to run for more than 3 hours at a time. If you're down in the south, like in Mississippi, Georgia, Florida areas, may not be the case. Your heat may not run that long. You might not expect it to in normal conditions. So I've actually seen this counted both ways. I've seen heating counted as continuous up north and not as continuous in the south. Motor loads, again, we're considering these non-continuous motor loads. Again, when calculating total loads that are considered non-continuous, such as motor loads, we simply use the total connected load at 100%. In the case where the non-continuous load is substantial, it is common to apply a diversity factor to this load that is not in excess of the total general receptacle load for the same feeder or service. So, in other words, if we have a really large non-continuous load and we have a large general receptacle load and we see that our total receptacle load is reduced by some percentage, we usually can apply that same percentage to our non-continuous. So, for example, in our previous example, we had that the total connected receptacle load was 18 kW, but the diversified load was 14 kW. So this was a total diversity of about 77%. So I would say I would feel comfortable diversifying this large non-continuous load at about 80%. I don't want to go below this number. I usually just round up to the next whole number when I do design. Non-concurrent loads. So there are also special cases where two different loads being served by the same panel cannot be energized at the same time. A common example of this is electric heat in a condensing unit associated with the same air handler. The controls in this case will only allow one or the other, but not both to run. In this case, the National Electrical Code will allow you to only count the higher of the two loads when sizing the panel and feeder. If it is unknown if they are concurrent or not, then both loads must be used in calculating the total loads, because there is a chance they could both run at the same time, though likely not. Kitchen appliance loads. So another very diverse type of load is that of kitchen appliances. It should be evident that in a kitchen, not all the appliances are typically being used at the same time. This being the case, the NEC allows an increasing diversity factor to be applied to the total kitchen load as the number of appliances increases. And so the table we use for this is 220.56. So you can see for one or two kitchen appliances, we got to count them 100%, but once we get to 3, it's 90. If we have 4 appliances, 80, 5, 70. And so you see this a lot in a commercial kitchen, especially if you did something like a franchise, like a Chick-fil-A, Burger King, McDonald's, we start to apply this. But also, you know, if a larger office building has a cafeteria, or a hospital sometimes will have a cafeteria, we can utilize these as well. And same things like a hotel, a lot of times they'll have a small kitchen located in it. So, you know, just be aware we can't apply these factors, the diversity factors. Of course, once you get to 6 and above, you know, it tops out at 65% diversity, but you can diversify all those loads, the total load, by 65% in that case. So there are some other demand or diversity factors you might run across. You know, if you're doing general calculations, you know, if we look at dwelling units, hospitals, hotels, warehouses, you can see they have different diversity factors. So in dwelling units, which would be like an apartment complex, the lighting, you know, the first 3,000 or less, we do it 100, but then you get up to 120,000, 3,000 to 120,000, you can diversify that quite a bit. And that's because, you know, in an apartment complex, you know, as the number of units goes up, not all the lights are going to be on all at the same time. Same thing in a hospital and hotel. It's kind of a similar scenario here. I've done quite a bit of hotel work, and I've definitely seen this firsthand. You know, they purposely don't occupy hotels at 100%. I think generally they try to keep a third of the hotel rooms vacant. I guess that's for cleaning purposes and all that type of stuff. So the first 20,000 or less, you know, we can diversify at 50%, because even the ones they are booking, they're not always booked out at 100%. You know, and then from 20 to 100, you know, 40%, and then if you get over 100,000, that's a pretty big hotel. You know, you're diversifying that down quite a bit. Same thing with hospitals. You know, as the load goes up, you can diversify the lighting, the general lighting load here. Another one we can look at is if we do optional calculations for multifamily dwellings. So, you know, if you square foot the thing and say, you know, 1 unit is going to have this much load on it, we can then add those units up, and then we can diversify. And this will be for the main service. You can really downsize that service quite a bit. You know, if you get up to 40 units in an apartment complex. You take the amount of load, total load that you have on one apartment, and then you multiply it by 28% to size the service. So, they realize that in an apartment, you rarely use every receptacle and every light all the time. It's always people going from one room to the next, turning things on and off, and people leaving their apartment and whatever, going to work for the day and all that kind of stuff. Another table you might use, and this again would be in an apartment complex probably, is clothes dryers. So if you have 1 to 4 clothes dryers, 100%, but then as we start to go up, you can see it drops down pretty quickly, and then when you get above 22, then they have a little calculation you can do here. And then when you get to 23, it's 35%, and so on and so forth. So, if you were to have an apartment complex with 50 apartments, you could take your clothes dryer load, you need to separate that out, and then you could say, take whatever the size of the dryer is, times 50 times 25%. Another method for calculating farm loads, I have to say this is the one, or 2 tables I guess I should say, that I have never used in my 30 plus years of doing design work. I've never done any farm work, so I don't have any examples for you directly, but just be aware that if you do farm work, there is a diversity factor that you can apply there. Another one they have is for electric ranges. So again, this would come into play for an apartment complex probably, or you might have this for a hotel if it has a kitchenette with a range in it. So here, same type of thing. You take the number of the appliances, and if it's 3.5 kW, then you can use this column. If it's 3.5 to 8 kW, use this column, and then use this column for larger, not over 12 kW. And again, you just multiply it by the factor there. Another diversity factor that's used in larger buildings that have more than one elevator is table 620.14. And so you can see that as the number of elevators goes up, you can diversify it more and more up until about 10. Then when you get to 10 or more, it tops out. And this makes sense, because not everybody's on the elevator going up and down all the time. So it does allow some diversity for that. So here's an example of a branch panel from a project I've worked on in the past. And so here you can see we have all different types of loads here, and the code here, it tells what designation it is, so it tells which diversity category that I'm putting each of these in. And so you can see I have R is for receptacle, and here's the definition over here on the side. So I have a certain amount of receptacle load, so the receptacle load here is not quite 4 kW, so that's not high enough that I can apply a diversity factor, so I have to take it all at 1 or 100% or times 1. You can see here I have a little over 17 kW in lighting, so I have to multiply that by 125%. So it goes from 17 to a little over 21. Do have a kitchen appliance here, a refrigerator, but there's only one of those, so I don't get to diversify that any at this point. And so this kind of a general layout of how a panel schedule will look. And so for each receptacle circuit, we have its own breaker, and we have a 20 amp single pole breaker. We have the load here, and then we size the branch circuit here. So we're not running any parallel, so it's just one set. So you'll have 2 phase conductors that are number 12. You'll have a ground that's number 12, and then the conduit is 3/4 inch. So you can take a look at that, and then you see over here we add the total up, so we come up with our using Article 220, our total load is 62.34, and so from that we can convert that to 3-phase amps, and this is applying all of the Article 220 diversity factors. We can also see how balanced our loads are, so we're well within the 10%, which most reviewers require us to have it within. And we had some future capacity, and so here's where we get the final 200, a little over 200 amps, so we would size it a 225 amp panel should be sufficient for the load in this panel. Here's an example of a switchboard schedule from the same project. So this is where loads start to add up, because you can see we're feeding multiple transformers, dry-type transformers that are feeding 208 panels. This is a 480 volt switchboard. So really each of these is basically a panel that we're feeding. And so you can see we add up all the loads from all those panels, and it starts to get pretty significant. So this is for a hotel. So you can see here for the hotel lighting, we've got 423 kVA or kilowatts of lighting using that diversity table we saw a few slides back. We can diversify that by 32%, so you can see it knocks that load way down. We have heating and cooling. Here we both counted those. Apparently they weren't non-concurrent, so I couldn't verify that, so I had to count them all. Couldn't take the higher of the two, and in this case there was some space heating that we anticipated would run for 3 hours or more. Sometimes they'll put little space heaters in the stairwell and stuff like that, and that many times can run for longer than that, so we did have to bump that up. They did have a small kitchen, and they apparently had 6 or more appliances in there, so I got to use the maximum diversity factor there, 65%. General lighting, another miscellaneous continuous. There are some loads that sometimes you know are going to run for more than 3 hours. A lot of times if you know a computer is going to be plugged in, a lot of times we'll count that as continuous because it's going to be on for 3 hours or more for sure. Then we had other general miscellaneous non-continuous, and you can see here the receptacles were 36, so that ended up being a diversity factor of about 63%. So because this was diversified, I went ahead and chose 80% just to be safe of the miscellaneous non-continuous load. I probably could take that down a little more, but just as a general rule of thumb, I usually don't like to go below 75 or 80% unless it's just a really, really large facility and a really, really large non-continuous load there. So there you apply all these factors. So we went from a total connected load of almost 2,000 kVA. After we applied all the diversity factors, we're down to a little over 1,600 kVA. So it knocked it down quite a bit. Once we do the conversion to amps, you can see that comes to about 1,980 amps. We put a little future capacity in there, it gets us up to 2230. So a 2,500 amp board should be sufficient for this service. And so that's how we sized all of that.